Hello everyone, welcome back. So this time we're going to try to calculate the moment of inertia for this composite section right here. Now what we see is we've got three rectangles is what it looks like to me. One here at the bottom, one here in the middle, and one here at the top. There's lots of different ways you can look at this. You could say it's one big rectangle. Now I'm actually subtracting out a smaller rectangle and then two small rectangles down here. Do what you wish. It doesn't really matter to me. However you define the areas, it's going to be defining how you do this. So try to do it in a way that simplifies it in your mind. Now, for moment of inertia, we need to know what the centroid is because we're always rotating around that centroid, or at least normally we are. And the issue we're going to run into right now is that, we don't know where that centroid is. So, well, to figure this out, we're going to have to say, I have to do some math. You're like, no, math. Yes, math. Terrible, terrible math. Okay, so I'll measure everything from the bottom of this little bar right here. And I've got to make my table. So my table, first I have the section number. Then I'll have the distance to their centroid, their area, and then the sum of that. The multiple product of that. I'm going to have three different sections. Top rectangle, middle rectangle, and bottom. Everything is measured from the bottom. So 1, 2, and 3. Okay. Now for this bottom little rectangle, since I'm measuring everything from the bottom, the distance to its centroid is ½ an inch, because it's going to be half that distance. Its area will be 6 times 1, and then multiplying those together I get 3. For the second one, the distance to its centroid from the bottom would be equal to, well, 1 inch, because that's going to the bottom of it, and then half of its height. Now it doesn't tell you what its height is, but you can do some math. That's 14 here. Subtract 1 from both sides, and we get that this is 12. So I go 1 plus half of 12, which would be 7. Its area is 12 times 1, which is 12. Multiply this together, and I get 84. My third one up here is the exact same shape as the middle one, just turned on its side. Its distance to its centroid would be, well, 13 inches plus ½ an inch, so 13.5. Its area is 12. I multiply those together to get, let's see here, 13.5 times 13. There you go, 13.5 times 12. 162. Okay. And then I add all those together, and what do I get? I believe what I'll get is 249 right here and 30 right here. Okay, my little sums. Then I remember that the centroid location is going to be equal to the sum of my area times their little centroids, that's the little y squiggly hat, over the sum of the area, which will be equal to 249 over 30, and it's equal to 8.3 inches. 8.3 inches. There we go. Now that we've figured that out, we have to move on to actually calculating the moment of inertia, which is not super easy. It's not honestly super hard either. So let's move it down just a little bit. Now luckily for us, all three of these are triangles. But unluckily for us, all three of these are not centered on the centroid. Like, well, what does that matter? It matters a lot. We have to use something called the transfer formula to figure this out. And that requires another table. So first off, I'm going to make my table. It's a bigger table this time. Ugh, it's huge. The first section will be number. 1, 2, and 3. That's for the three different rectangles. And then I have a bunch of different things. First off, I calculate, well, what is theirs around just them? What's their moment of inertia just by themselves? And then I need to figure out what their area is. Then I have to find the distance from their centroid to the actual centroid. And after that, I multiply those two together. And then finally, with all that, I can then calculate the total moment of inertia. Okay, the total moment of inertia. X not there. Okay, lots to do here, lots to fill in. Now the equation for the moment of inertia is the same for all of them. They're all rectangles, and so Ix naught is going to be equal to base height cubed over 12. And remember, because my little axis is going from right to left, the base is always the dimension that is parallel to that. So this one for this one, this little tiny piece right here, and then 6. So for the middle one, it's actually the base is going to be 1. Don't get confused with that. Okay. So for that bottom triangle, its base is 6, its height is 1, and it's over 12, so that'll be 0.5. Its area is simply going to be 6. Its distance from its centroid to the actual centroid is, remember that this distance right here is 8.3, and its centroid is 0.5 above the bottom, so its distance would be 8.3 minus 0.5, which would come out to be a distance of 7.8. I multiply that together, AD squared, which is from the transfer formula, and I get that that's 365. Then finally, I add my initial moment of inertia to my, with AD squared, to get my final moment of inertia, which is 365.5. So by itself, this doesn't have a big moment of inertia, but for the overall product, it's actually quite considerable. Okay, so for that middle one, for that middle rectangle, right there, it's got a height of 12 and a base of 1. So base 1, height 12 cubed, all over 12. And that would come out to be 144. 144. Its area is 12 times 1. The distance from its centroid to the actual centroid, remember that its centroid is halfway its length, so that'll be 1 plus 6, which means it's 7 from the bottom. Centroid is 8.3, so 8.3 minus 7 is 1.3. AD squared then comes out to be 20.3. It's not much. And I add it all together, and what do I get? Well, I get 144 plus 20.3, which is 164.3. Okay. And finally, I have that top one, which is very similar to my middle one. It's the same dimensions, just on its side. However, when it comes to moment of inertia, that changes things drastically. So what I'll get then is going to be, well, its base is going to be 12. Its height is 1 cubed. That's all over 12, which means that it only has a moment of inertia. It's a very, very small of 1. Its area is 12. And then what's the distance to its centroid? Well, we know that it is way up here, and it's 13.5 inches from the top. And so I would do is 13.5 minus 8.3. If you're wondering, wait a second, it shouldn't be 8.3 minus 13.5. That's how you've been doing this entire time. It doesn't actually matter because it's going to be d squared in the end. You can do what you want. It doesn't matter if you get a negative number here. And so I do that, and what do I get? I get 5.2. 5.2. Okay. I'll do AD squared, which comes out to be 324.5. And then I add that to my original one, and I get 325.5. And what you see is that that little small section right here is actually the one that's going to be contributing the most moment of inertia. Because now when we want to calculate our moment of inertia, all we have to do to solve is simply add all of this last column together. And what we will get then is that it is 855 inches to the fourth. And we're done. 855 inches to the fourth. Now, a second thing we could have done is to do it around this vertical axis. You can also calculate moment of inertia around that. It's much simpler because you don't have to use the transfer formula, because they're all their centroids are centered on that axis. So I'll let you try that on your own if you want to. But I hope this helps you. Thank you for listening. And remember, these tables are your best friends, so try them out. Have a wonderful day. Bye-bye.